normally, and we'll have time for more discussions and more questions. And we start with Jerzy. We'll talk about the quivers and the potential interest for electricity.
That's right. So I was asked to give some kind of an introduction to quivers and semi-invariants. But as far as the time is concerned, I mean, if you have enough of me, you can always throw me out, right, at any moment. So just, you know. All right. So, all right. So quiver is directed graph, okay? So let me just do some notation. So quiver will be Q0, Q1. These are vertices. Finite number of vertices, so it usually will be 1 through some n. And Q1 are arrows. And the kind of terminology I'm used to is just that every arrow has its head and tail. And of course, HA and TA are in Q0. And the point is to define, so that's the first thing. So it could be something like, you know, you allow loops, for example. That's right. You don't impose any commutative relations whatsoever. No, nothing. So then we fix a field K. Maybe K is a algebraically closed field. Maybe we can think it's complex numbers. And we define this category representations Q. K. So what is V, a representation? It will be just associating to every vector space, every vertex vector space, say V1, V2, V3, V4, and to every arrow, you just associate the linear map. Everything is here finite. We will always assume those are finite dimensional vector spaces. So, so you know, you would have for representation of this quiver would be just, well, 4 vector spaces and 5 linear maps. So if you fix bases, you can really think of representations as matrices. And notice that such V has a dimension vector of V. It's a vector, dimension V of X. So we have this space Z to Q0. We can think of them as being the space of dimension vectors. All right. So that's, I think, elementary. No questions. Yeah.
The X is V sub X.
Excuse me?
Yeah, X is
Oh, yes. Thank you. That's right. All right. So now we can look at, you know, if we fix dimension vector, we take this set of rep Q alpha, representations of dimension vector alpha, then it becomes a representation. I have a bunch of matrices of fixed size, and then I can change bases at every vertex. So there's this group GL Q alpha, which is the product of X in Q0, GL alpha X, and it acts on it on every matrix by a row and column operation. So this is GX on like VA will be, I think, what? GHA VA GTA inverse, right? So we get this family of representations of those reductive groups. And I guess our interest in the complexity, this is a little different problem than what Ketan was talking about, because here the quiver is fixed, but you know the dimension vector will be changing, right? So we have different groups. We have infinite collection of different groups. All right, so now I should also point out, no, I didn't say this, that this is a category. I didn't tell you what is, I did not define the morphisms. So let me define hom Q VW for V and W in the rep Q. So we have two representations. I want to define what are the homomorphism of representation. So we get a nice category. So what is it? So here we will have the collection F, which is collection of linear maps Fx from Vx to Wx. But we need a compatibility. So, so because something has to be, those arrows have to have some meaning. So what we need is that for every A in Q1 now, if I have such collection of linear maps, I can form this square. I have VTA, VHA. This is my map V of A. Then I have the same for W. I have WA. But now I have my maps F. And as you can guess, we require that all those diagrams commute. Then you get the map of representations of the quiver. So, if you have the simple quiver, Q, just two vertices. I skipped the example with 1 point, okay? But anyway, so a representation is just a linear map, V of A, and a morphism of representations is a commutative square. So we've seen that problem before, of course. So now, all right, so this is a nice category, and this rep Q is abelian category. In fact, these are, KQ modules. So there's an associative algebra of path algebra. I don't know. I won't define it at the moment. And so there's a category of module over some associative algebra. And this means that the Krull-Schmidt theorem is true.
U here is fixed, right?
Excuse me?
U is fixed.
Q is fixed, that's right, and the field is fixed. Q is fixed, and you change the dimension vector, right? You consider representations, yeah. And, maps between the representations, right? Yeah. Krull-Schmidt, so it means every, we have a notion of direct sum. If you have two representations, there's an obvious way to define the direct sum. You just put direct sum on every vertex and direct sum of maps. That's right. So Krull-Schmidt tells you that every representation decomposes uniquely up to whatever permutation to indecomposable representations. All right. So now I'm supposed to talk about semi-invariants. So you can also talk about, you could take GL invariants, at every, well, okay, let's see. So let's talk about semi-invariants. So here I'll make this assumption that Q has no oriented cycles. It's one can get rid no oriented cycles. So it means at the moment also no loops, for example. So something like this is not allowed. Okay. One moment, yeah. So now you see we fix dimension vector. We fix dimension vector alpha. And now I have this rep Q alpha. And this is just a big affine space because each arrow gives me a matrix. I have a bunch of matrices, right? So I have so it's a product over A and Q1, K to the TA cross HA, right? So this is the affine space. And now I have my group. But now you see, if I have no oriented cycles, then let me just tell you right away, I will not have any GL invariants. Because basically, if I have any representation, I can scale it. 0 is in the closure. There will be no constant GL invariant. So we take so-called semi-invariants. So what is a semi-invariant? Well, so I choose a sigma, which is in some Z to Q0, or maybe let's say character of GLQ alpha. But we know that characters of GLQ alpha, at each vertex you have just power of determinant. So this is Z to the Q0. And now I define semi-invariants of weight sigma. And this will be just the set of all polynomial functions. So these are, polynomials is the entries of our matrices. All right? Such that for every G and this GLQ alpha, I have that now G times F. We know that this group G acts on the functions will be basically sigma on G times F. So the function transforms with the character of the group. Okay? Let me give you the simplest example. Well, we have to take the same quiver Q, 1 to 2. Then, of course, if I take the dimension vector alpha to be nn, then, well, V goes to determinant of V, of A, will be a semi-invariant. And I like to think of this as being of weight. There are two competing notations, but usually I do this 1 minus 1. So here it will be will transform with product of the determinant there with the determinant inverse. Some people use negative notation, but it's just cosmetics. Okay, so let me just do this. So this means it transforms with the power of determinant on the vertex 1 and the minus. With minus 1 and the vertex 2. Anyway, notice that if alpha would be different than, so alpha 1 is different than alpha 2. I have some nm where m is different than n. Then there will be no non-trivial semi-invariants, no semi-invariants. So that's very easy to prove. So somehow you see what happens is that depending on the dimension vector, you can have more or less of those semi-invariants. Okay, so that's the definition of semi-invariant. And so the result that I want to show you is that you can, for each quiver, you can write this kind of canonical spanning set of the ring of semi-invariants, which kind of corresponds to representations. Okay, but before I do that, let me introduce even some object related to the quiver, so-called Euler form. This is just a non-symmetric bilinear form that kind of encodes the quiver for you. You could say that quiver is the same thing as this. So this will be the form that acts from the ZQ0 times Z2Q0 to Z. And basically alpha beta is summation over all vertices alpha x beta x minus summation over all arrows alpha ta beta ha. So the way to think about it, we have the matrix of this form. In canonical, you have coordinate basis. So you see, let me just do the example and everything will be clear. Suppose I have quiver 1, 2, 3, AB. What would be the matrix of this Euler form? Basically, you see, I put 1s on the diagonals. And at each entry ij, I put minus numbers arrows from I to j. So I would put here -1, because there's an arrow from 1 to 2, arrow from 2 to 3, 0, 0, 0. So that's the matrix of this Euler form. So really, it's obvious that every quiver will be, you see, since there are no oriented cycles, then like for each ij and ji, one of them will be 0. At least one of them will be 0. So there will be no ambiguity of any kind. Okay. So that's this Euler form. And this will be important.
It's like the Laplacian.
Yeah, that's right. And there's also something the so-called Pitts form, which is alpha beta plus beta alpha. Symmetrization, this plays an important role. Well, so, all right. So now, what I'll give you the spanning set, spanning semi-invariants. So what we'll be doing, I take rep q beta, and I want to calculate, you know, this SI q beta. I want to tell you what spans this set. But the way I'll do it, I take now a representation V of dimension alpha, and to each V I associate under certain conditions, I'll associate a semi-invariant CV here. And then the idea will be that those CVs will be spanning semi-invariant. So the element from this rep QW I will denote by rep Q beta, I'll denote by W. So I'll show you what is the value. I have to tell you what is CV evaluated at W. So the point is that when you have two representations, kind of the underlying thing of this Euler form, there is a so-called canonical map, or some Ringel map, some people call it. So let's take V in rep Q alpha, and let's take W in rep Q beta. Two representations. Then I have the following map. I can take direct sum over x in Q0, hom over k from Vx to Wx. This will be my map dV, W. Direct sum over the arrows, and I take hom over k from VTA to WHA. So you see, so here, so what's the map? So now I start with some family, phi x. Now I do not assume that they commute, just any family of linear maps, but I can draw the same diagram. So I have VTA, VHA, WTA, WHA. So here V of A, W of A, and now I have here my arbitrary maps, phi TA, phi HA. So now where does this map go? Now I need to produce a map from here to here. So there's kind of one way to do it, right? Well, you have two ways to go, so you take a difference. This way minus this way. So it goes to the family such that phi HA W VA minus WA phi TA. And you see, notice what happens now, this is kind of nice, is that of course you know what the kernel of this map is. Kernel of this map is, of course, by definition, hom Q from VW.
Decide on the sign.
Excuse me?
How to decide which one to go
Take your
with the
pick.
plus and which with a minus?
Take your pick. Just one has to go with the plus, it doesn't matter. The point is that the kernel is hom QVW, because exactly the kernel will be the commuting ones, the ones that go to 0. Okay? And for those that know a little bit about homological algebra, this will be what's called XQVW. So you see, well, anyway, yeah. Well, one could actually say, you see, you have V and W, VHA plus WHA. So you can now, you see, you have, if you have an element here, some psi A, so you have here V of A, W of A, but now you write this psi A. So this will define you a new representation, and W will be a sub-representation, and V will be a factor representation, so you get an extension. So anyway, so this will be, and also notice what I should, the important thing. Yes, but the point is that these are hereditary path algebras. There's no x2. That's right, it's x1, but there are no x2, no x3, and so on. That is the whole. So now you know everything about homological algebra over KQ. That's right.
So there's x before there's x1. But so they people talk about x before they realize they can take x1, x2.
Notice also that if I take dimension of this minus dimension of this, I get exactly the value of the Euler form. Because here I get product of alpha x times beta x sum and minus this. So you see this Euler form is an Euler characteristic, okay, of two representations. So that's what happens. All right. So now that's enough of definition. So now we can define this CV. So you see, now I come back to this situation. I have my rep q beta, and I want to define some semi-invariant. So of course, how do I do it? Well, the easiest way to define an invariant is to take a determinant. The only thing I need to know is that this matrix is a square matrix. So I just take those v's for which this matrix is a square matrix. So now I fix q, I fix my beta, and I'll describe you semi-invariant. So take v of dimension alpha such that alpha beta is 0, which exactly will mean that this will be a square matrix. All right? And then you can define the semi-invariant. CV will take W to determinant of this dVW. I'm cheating a little bit.
Yeah, because determinant is not.
That's right. This is defined up to scalar. So one thing, I don't care. I define up to scalar. Or the other is I just take some framing. I fix some basis of my spaces at dimension beta at every vertex, and then I have a determinant. So in this way, I define my semi-invariant. So in particular, just a silly example, this one arrow.
So that's supposed to be a function on rep.
That's right.
Oh, on rep q alpha. I see. Gotcha.
It's a function on rep q beta, taking W to dVW. That's right. And actually, so the proposition is that CV is an SIQ beta. It's a semi-invariant. And actually, the weight, let me just say it. I mean, it's not difficult to show, but the weight is a linear function that you will get when you take Euler form and put alpha on the first coordinate. Okay, this will be a linear function on ZQ0, so it will give you a weight, power of determinant at some vertex, at every vertex, and then you get. So let me show you two examples.
Fixing v and running over w.
Exactly. I fix v and I move w around. I get semi-invariant. I could do it the other way, okay, but doesn't matter. Yeah.
So I don't understand.
Well, weight. It's putting the dimension of alpha on the first coordinate. All right. Let me just give you the example.
Alpha comma beta.
Excuse me?
You mean that there is no on QVW must be 0, otherwise you get 0.
Yeah.
That's right. So this also, well, I mean, the theorem, when I state the theorem that this spans all the semi-invariant, it will mean that for all weights which are not of the form alpha slash, where alpha is non-negative vector, clearly there will be no semi-invariance. That's what it means in particular. That's right.
This proposition not only states that this is a semi-invariant, but in general.
Right now, I state proposition it's a semi-invariant, but then the theorem is, that's right, theorem, the ring SIQ beta is spanned as a vector space by semi-invariants of form CV. So this means that, you know, if sigma is alpha slash, then SIQ sigma, Q beta sigma is spanned.
So the only pairing you have is between these dimension vectors.
Yes.
So why is sigma alpha such? Because alpha is
That's right. So
alpha paired with beta is 0.
yeah, if sigma is of the form alpha slash such that alpha is not orthogonal, also you don't get semi-invariant there. Okay? Just, well, you will see in a second. Let's see when I do the example. If you think about partitions and Cauchy formulas, the boxes wouldn't add up if there would be no orthogonalities. It's just some simple thing, okay? But so it's spanned by CV. If not, SIQ beta sigma is 0. And also alpha beta is 0, I should write. If so, the sigma is of this form, with alpha beta, the scalar product being 0, then you get the spanning set. If not, SIQ beta sigma is 0. All right, that's the statement. So example, take, well, you know,
I don't understand. You say it's alpha slash. So you put something in the second coordinate. What goes in the second coordinate?
Oh, this you treat as a function from on a. You put on the second, you put the coordinate vector to get the value of the vertex. You put the vector which is 1 at the vertex and 0 everywhere else, that you get the value alpha x. Yeah. So alpha slash on x, I think, is alpha epsilon x, where epsilon x will be the coordinate dimension vector. Yeah. All right. So let me just. The best thing is to see two examples, and it becomes really obvious what's going on. So let's take this silly example, this one. So the Euler matrix is 1 minus 1 0 1. I should point out that this what is in decomposable representation of this, okay? Everybody knows this because this is a theory of linear maps, right? With up to row and column operation, so you know that the only invariant is the rank. So this means that every linear map from k to the m to k to the n, I can write as r times identity from k to k. Basically, I reduce to the form I0, 0, 0, RR, and plus m minus r times the vector in the kernel plus n minus r times the vector 0, k, right? So really, this will be the building blocks. I should point out that there is a, if you have direct sum, CV1 plus V2 is CV1 times CV2 or 0. So this one can just. So anyway, so you see, the only thing is that so the only semi-invariance that you see, determinant V of A, is of weight 1 minus 1, which is the first row of this thing, okay? Which means that it's something putting the dimension vector 1, 0, comma slash. So this is C of the representation K0. And you could see it from the definition also here. Because let's just run the definition. What is, when my representation is K0, let's just do this linear map. So I have now Q is 1 to 2, A. So what do I have here? So I have V1 equals K, V2 equals 0, right? I have two vertices. V1 equals K. So of course I have here, I have W1 because I have home from K to W1 plus home from 0 to W2. And here I have W2 because there's home from V1 to W2. There's only one arrow. And if you trace it through, well, you will see that this is a matrix WA. So that's right. So, well, WA I should write because this is a function on those W's. All right? So these are semi-invariants. There is another form of Domokos-Zubkov, a different form of semi-invariant. Basically, they said something like this. So I have now semi-invariant rep Q beta. This is very different, and I want to define the semi-invariant. So you see what you do, you take all block matrices, so the linear maps from, I don't know, some W1 plus, maybe WX1 plus, no, here, WX1 plus WXP, and here you put WY1 plus WYQ, such that this is a square matrix. And then in IJ entry, Wxi, Wij, you put some linear combination of W on all the paths in the quivers that go from I to J, okay? In whatever way you want. So you have I and J, you might have, several paths in the quiver, so you can, of course, then, if you have a representation, you can define what is the W on the path. It's just the composition of those linear maps. So you just take basically combination of with some coefficients, okay, of W paths. You take any such block matrix, you take determinant. It will be a semi-invariant, and they also will, they will also span. So that is kind of two different forms. This is directly relates to representations. It's not difficult to show also that they're equivalent.
Sorry, and then what is this sum?
Yeah, so you see, I want to define a semi-invariant, right? So I take a linear map I have a representation W. So I take the direct sum of the spaces at some vertices, maybe with repetitions, and here and here. And so here I have to define the homomorphism from this WO. It should be from Xi to Yj, I should say. So you take a path from Xi to Yj. So of course, for every path, you can define what is a W on a path. It will be composition of W on the arrows of the path. So you take some linear combination, of those paths, W on those paths. Like, for example, I had this W1, W2, right? So this is just 1 by 1 matrix, If you have a quiver, I don't know, 1, 2, 3, 4, let me just say, you could take W2 plus W3 going to W4, for example.
Sum of the compositions over all paths from...
That's right. You have a choice. You can take one composition. You can you produce many determinants in this way, right? And each such determinant will be a semi-invariant, and those will span. So block matrices basically, which are square, that you can produce from W. Yes.
So this WP is the path.
It's a path, yeah.
And you can put just any coefficient in front.
That's right. You can have many paths, and you can take linear combination. Yes, you had a.
The two sets of determinants, the two sets of trials are equal or not?
No, these guys will be like linear combinations of those. Basically, if you take a generic representation and you take coefficients of the variables of your matrices, the representation V makes them variables, coefficients will be like that. Basically, that's what will happen. Okay, so and the other way you can also go. Okay, so there are those two interpretations that are, I don't know, each has advantages, each has disadvantages. I don't say that one is. Okay. Okay, do you want to throw me out, or can I say one more thing?
I think tail bite should be included.
That's what I want to say next. So, okay. And then I go, okay. So that's right. There's also trichotomy. Trichotomy and the representations of quivers.
So where was the dichotomy?
I will talk about it. Trichotomy.
But I thought before trichotomy comes the dichotomy.
Yes, so trichotomy will be a subdivision of dichotomy. Yeah, okay, so trichotomy. We have, so basically we look at the representation, we fix Q and we look at rep Q. And now the question is, how many indecomposables do we have? Can we describe them? Okay? Indecomposables, yeah. So there are three possible behaviors. First, finite representation type. So, finite number of isomorphism classes of indecomposables. For example, our one arrow quiver had 3 indecomposables, right? So it was in this class. Second, so this is finite representation type. Then tame type. There are at most 1 parameter families of indecomposables. And 3,
There are at most one parameter.
so in each dimension vector, you will have, several maps from the projective line. And this such that there will be some discrete set maybe, and that's right.
So it's one-dimensional.
Just one-dimensional, yeah.
It means that the parameter space of indecomposable modules is a one-dimensional variety.
No, so
Just even a bunch of lines and a bunch of points. It has to be rational, yeah. Union of lines or points in every dimension vector.
One-dimensional is still.
With me?
It's still one-dimensional.
Yeah, one dimensional. That's right. And the third is a wild type.
For each dimension D.
So this means that actually, technically speaking, that the modules over non-commutative rings in 2 variables embeds in rep Q by some, I think, exact and faithful functor. So this would mean that if you would have a hope of parameterizing completely all the decomposables, this would mean you would, at the same time, as a subset, maybe very bad subset, but as a subset, you would see, classifying 2 loops, up 2 matrices up to conjugation. Okay?
For the second, that is only for domestic dimension type. So for each dimension, you have to choose one parameter differently. So I think you should say that for each dimension D, because you cannot choose uniform one parameter.
Okay, but we are in like hereditary case here. Okay, so it's a very easy. Yeah. I'm not talking about quivers without. That's right. The same is for kind of arbitrary K algebras, right? Associative algebras. There is the same. So it's a very deep theorem that this trichotomy occurs, right? That if 1 or 2 is not satisfied, then 3 is satisfied, which is Drost theorem. That this thing occurs. Okay. However, for quivers without relations, just representation of quivers, there is also, it's known that there's this Gabriel theorem, and that the first thing occurs for Dynkin quivers, simply laced quivers. So it will be AN, DN, E6, 7, 8 with arbitrary orientation of arrows. That's right. So this is another kind of surprise is that all those concepts do not turn out not to depend on.
So it doesn't depend on orientation.
Finite representation type is precisely when it's AN, DN, or E6, 7, 8 with n orientation of arrows. And actually, number of indecomposables is even also of indecomposables. And their dimension vectors are in bijection with positive roots of the root system. So, for example, you see if you have the graph of type AN, then the indecomposables will be always, doesn't matter, connected string of ones. And so basically you put K here, identities are on the arrows, and these are all the indecomposables. And this corresponds to the fact that, the way you write the positive root, it's a combination of simple roots. This will give you dimension vector. And so it does not depend on the orientation of arrows where the decomposable occur. So at first sight, it seems unbelievable, right? But, well, that's what happens. And for the tame ones, 2 happens for extended.
So there is no G2 here, B groups?
No, simplest. You can get, it means no multiple, one length of roots. No long roots, no short roots. Okay? So you could have you could have like two edges, but
That's precisely the set, right?
that's right, precisely the set,
Yeah.
precisely.
First type.
If and only if.
Exactly.
That's right. Exactly, yeah, that's right, exactly. And second type, exactly for extended Dinkin quivers,
Extended, simply laced.
simply laced. Yeah, I will. So for AN, it's just, you know, you put one additional vertex in this.
But then it requires a cycle.
Well, you assume that the orientation is such that there's no cycle here. Then you get dn, you get this, and then E6. You have to add the one edge here, so this is AN hat, or AN tilde, this is DN tilde, E6 tilde. For E7, you add the thing here. Basically, what you have to do the things that I did the diagram of representation in my previous talk. You add the black dot where the adjoint is, okay? So and then E8, you add it at the other end. So you added the extra guy here. Here you added the extra guy here. Here you added the extra guy here. That's right. And also here, I mean, one can say much more. In each of those cases, you have one root which is so-called alpha isotropic root.
The imaginary root.
That's right. And basically there is exactly one family, one parameter family of indecomposables for every dimension M alpha. There's exactly one parameter family of indecomposables.
For every N alpha?
For every M. Yeah, it's like Jordan form. You see, if you would have for Jordan form, so it's just one loop. Actually, it has a cycle, but okay. So, of course, indecomposables are the Jordan block with eigenvalues. So, in each dimension M, you have one parameter family of indecomposables.
Countable one-dimensional families.
That's right. So you have just, in multiples of one vector, you have one parameter families. Otherwise, you have many others. But yeah, that's right. And then the last thing that I want to say is the cut theorem. So by the way, okay, so this means, you have those lists. So this means like this, what I said about CVs. I mean, if you have now a tame quiver or Dinkin quiver, and you have dimension vector, it's very easy to write down the semi-invariants, because you just write all in the composables. You see which of them have dimension vectors orthogonal to your dimension vector. You take those CVs, and that's it. So you have, finitely many generators, and they are all polynomials. So it becomes very easy. And in fact, only for generating semi-invariants, it's always enough to take those. So somehow, the dimension vectors from which you take, the generating semi-invariants for tame quivers are even bounded. Okay, so from complexity point of view, these are like really easy cases. I think it will be probably some, I don't know, maybe even linear time is clearly easily polynomial. There's just no difficulty, I think, at all. However, of course, for tame quivers, for wild quivers, you don't know which indecomposable to take, and those dimensions can grow, and that's actually a problem. That's exactly the problem, because as Abi said, one of the simplest examples of wild quiver is this guy, right? That's really one of the basic ones. So last thing that I want to say is the cut theorem, which is very generalization of this. So if you have any Q, and you look at the set of all alphas such that in the composable representations, there's some in the composable representation in dimension vector alpha. Okay, so this set does not depend on the orientation of the arrows. That's right, does not depend on orientation of arrows. Okay, so this is, and the interesting thing is that There's no proof of this theorem that does not go through Y conjectures and characteristic P. So all dimension vectors alpha in the ZQ0,
Not empty.
that's not empty, that you can find in the composite representation. Not empty, that's right. That's right. Well, then complement also, if I would write Z, oh, not empty, yeah. No, well, actually, okay. If it's true for one, it's true for the other, right? Yeah, that's right, okay, sorry. And actually, these are supposed to be, you know, the roots of corresponding Kac-Moody algebra. And that's what he proves, that's right. These are exactly the roots of the corresponding, you know, some huge infinite dimensional algebra. Okay, so with this, I think I go away. And
Thank you very much. Unless there are
What you said about the Weyman conjectures?
there's no proof of this Kac theorem that does not go through counting over finite fields and so on and so on. So there's no direct proof over C of this fact, for example. One would like to have such a proof.
That's right. So what it costs to reject?
Yeah, in 1982 or 1980.
Like used Weyman conjectures?
Yeah.
What's the relation with?
What's at this conference?
So the question that I think Ketan wants to discuss is, if you fix a quiver, can you find an algorithm to calculate all those rings of semi-invariance, which is polynomial in the dimension vector? Okay? In the dimension vector. So from what follows from this is for tame quivers and Dynkin quivers, for those simple quivers, it's a very simple problem because the generators will come from the decomposable you can list and they occur in very low degrees. Okay? So that's, yes. And Ketan will tell you the rest.
Is there any description of the linear relations among the semi-invariants in either the first type, the second way?
Yeah, there is a description of relation which is kind of like for GL invariant for quivers with, you know, with loops, then you have this thing that all the relation between creation of matrices come from Hamilton-Kelly. There's an analogous statement of that type, but it's kind of, you know, not very useful because you never know in which way they occur.
But not for conical.
Oh, for tame and Dinkins are all described completely.
Impossible to see?
They are all polynomial rings or hypersurfaces. Okay, so yeah, that's right.